In this video, we're going to talk about spontaneous or thermodynamically favored redox reactions and Gibbs free energy. Now, I'm in the library, so there's a little bit of background noise, so hopefully that won't interfere with our video. Now, we can use our standard reduction potential value to determine if a reaction will be spontaneous or not. Remember, thermodynamically favored means spontaneous. If it is not spontaneous in one direction, it will be spontaneous in the other. So we can look at our reduction at the cathode minus our reduction at the anode. If the value is positive, then it will be spontaneous, and if it is negative, it will not be spontaneous. This method for making predictions is useful because we're not given the activity series on our AP exam, but we will be given the values for the reduction potentials on the AP exam and the problems that you need it for. So by using this formula here at the bottom, this is the same one that we used in one of our previous lectures. In the table of standard reduction potentials, we can determine if any redox reaction is spontaneous. Remember, if the value is positive, the reaction is going to be spontaneous. Now, in this reaction, the forward reaction, we can see that our lead is being oxidized and our barium ion, our barium plus 2, is being reduced. Now, don't forget to change the sign of your reduction potential for lead, because we're looking at oxidation, not reduction. Now, this reaction is not going to be spontaneous because we have a negative standard reduction value. So let's talk about how this relates to our Gibbs free energy. Remember that Gibbs free energy has to have the units of joules per mole, and the EMF, or the cell potential, is in volts, which is joules per coulomb. So we've got all of our constants here. You can look at those. Remember that as you can determine if it's spontaneous or not by looking at the EMF values. Faraday's constant is positive, and the number of moles is going to be positive. So this is why there's a negative sign at the front of the equation. If your cell potential is positive, meaning that the reaction is spontaneous, then you have to multiply by -1 in order to make your delta G value negative, which also means that the reaction is spontaneous. Faraday's constant is the amount of electrical charge on 1 mole of electrons, and this equation and Faraday's constant are given to you on the AP exam. So in this example, we're going to find the Gibbs free energy and our equilibrium constant for this particular reaction. So if we look, the reaction for manganese runs in reverse. It's an oxidation, not a reduction. So we have to change the sign. The voltages do not change, even though both of our reduction half reactions are multiplied to balance the equation. Remember, volts is joules per coulomb, so if the number of electrons or the charge is doubled, the potential energy also doubles. That ratio stays the same. So in our first step, what do we need to do? We're going to find our delta G. So we substitute in our values for reduction and oxidation. Remember to change that sign for your oxidation. So our value is positive 0.44 volts. So that means that this is a spontaneous reaction. So our value is positive, means spontaneous. So our next step is going to be to find out how many electrons were transferred. And we look at our half reactions for that. Okay, so the units for the EMF were written in joules per coulomb as opposed to volts to make it easier for us to look at. So we use our delta G formula, we plug in all of our values, and we end up with negative 250 kilojoules. A negative delta G value also tells us that this is a spontaneous process. Now our next step is going to be to find our equilibrium constant. So we have this formula that relates delta G and our equilibrium constant. So we plug in our values, make sure that your units will cancel by using joules here. Okay, so remember that R is going to be 8.314 joules per mole Kelvin, and your standard temperature is 298 Kelvin. So when we plug this in, we find a K value of 6.6 times 10 to the 43rd, which means that our equilibrium is going to lie very, very far to the right because K is very, very large. Okay. Now let's look at our EMF value under non-standard conditions. Remember that standard conditions are 1 molar and 25 degrees Celsius. Your cell can only remain under standard conditions for a brief moment in time. As your reaction proceeds, your reactants are going to be consumed and the products are going to be formed. So in doing this, your concentrations or your partial pressures, if we have gases, are going to decrease in the reactants, and the concentrations of your products is going to increase. This is going to cause your voltage or your EMF to decrease. So you can see why the voltage decreases as the system approaches equilibrium by looking at Ohm's law, which is talks about the resistance. It's voltage divided by current. That value always remains constant, but that's beyond our scope. So the EMF or your voltage is going to decrease as the concentration of the reactants decreases. Okay, so your EMF value is going to decrease until you end up with a voltage of 0. So this is when this happens, this is when your battery dies. Okay, your cell is dead. Your voltage cannot go on anymore. So here we've got a system that was under standard conditions, and we add silver ion. So the silver concentration is now greater than 1 molar. So the rate of the forward reaction is going to increase, the voltage is going to increase, and your electron flow or your current is going to increase. Now we haven't established equilibrium yet when the cell is at standard conditions, but we can still apply Le Chatelier's principle. The more concentrations of the reactants increases, the greater the rate of the forward reaction, and the more the concentrations of the reactants decrease, then the slower the rate of the forward reaction. We're not going to consider our reverse reaction here because the electrons can't flow from the cathode to the anode. The more the concentrations of the products increase, the slower the rate of the forward reaction. So the more the concentrations of the products decreases, the greater the rate of the forward reaction. Okay, again, we're not considering the rate of our reverse reaction because we can't go from cathode to anode. So if we have a cell that's originally under standard conditions, functioning according to our equation we have here, until your zinc concentration is 1.14 molar, we're going to find the concentration of gold. Now what we can do here is just simply use some stoichiometry, some dimensional analysis. Oh, sorry, let me go back. Alright, so the change in concentration of gold, we're looking at our molarity of zinc here because that's increasing, and the concentration of gold is decreasing as our reaction proceeds. So we have our mole bridge here. So our new concentration of gold is going to be 0.093. So we know we started at standard conditions, which is 1 molar. We know that it decreases by 0.093 molar. So our new concentration for gold is 0.907 molar.